Okay, everyone, welcome back. Hope you had a good break. Short, but good. So before we start, a few things. I did send you the midterm survey. I don't need to see your individual responses. Don't send an email to me. Send it to the TAs. They just fill one single form with how many people are in column 1, 2, 3, 4, and 5, and I'll just look at those, okay? Yes?
You just email it to them?
Yeah. You don't need to print it out, because I think it's dangerous. They may get lost. Yeah. Well, either way, you can do both, but emailing is probably okay. Yeah. And please, by Friday, I think that's plenty of time to fill up a form with a few X's here and there. Kennedy Space Center. So it's on the 22nd, Tuesday 22nd, at 10 a.m. I'm leaving from the commuter lot on Gale Lemeron, and the guy will meet there at about 1 p.m. with us. So there is no organization behind this. Who wants to go can go. We meet there, we pay the entrance, and it's an unofficial tour of the orbiter because he has worked for 18 years on the Atlantis. So, yeah.
So you'll be staying on the campus?
Oh yeah, it's the visitor. Yeah, it's the visitor area. It's we're not gonna go. Yeah, if you want to go inside real NASA, you need to get badges, and it will be a nightmare.
Oh no, I just meant because there's tours, like fun tours like that.
I think with the entrance ticket, as far as I remember, there is the basic tour that you can always go on, and they show you around a few places. Does it stop? I don't think it stops.
It shows you launch complex terminal.
Right.
And then it drives you. You end at the Saturn V Center.
Okay, yeah, that makes sense. Yeah. So that's the basic one that everybody can do. And then I probably stay overnight because this is a research sponsor and he wants to meet with me and some students for dinner. So we'll probably just stick around and try to see the launch. But I'm not trying to organize this as a group because, as I told you in an email, I tried in the past and I have failed miserably because only 5 people showed up. So it's not really worth to go through all that pain. And it's really $50. You go there and who is there, who is not, it's fine. So you guys should get organized about cars. I think I have 1 seat at this point, maybe. But again, I'll probably stay overnight. So, yes?
Will we be able to attend the launch together and stuff? Or
we can. So that is the variable he mentioned. He said there is a way to see launches from inside where you pay a little more and you're a little closer than just going to Cocoa Beach, for example. But he wasn't sure if he could organize that. So I'm not relying on that, which means we should probably just agree on a beach there and go. I've done it in the past. You know, they don't close some of the beaches on the Space Coast. You can go. Yes?
He might be talking about the Saturn V Center.
Yeah, but I think you have to pay more if you want to stay for a launch, especially, you know, over at night. I think you have to pay an additional. We'll figure it out when we get there. I'm sure they will have it posted. I don't know, but yeah. So it's, you know, I'm trying to keep it simple. We go there. Who wants to stay and has a car and, you know, plans to stay can stay. Who doesn't want to see the launch can take off. Launches are always dangerous in the sense that they may abort. You know, SpaceX, the one I mentioned a few weeks ago, they aborted it 3 times, and they ended up launching on the 4th, I think. So there's no guarantee that it's going to happen, as you know. Yeah.
That 3rd attempt, I was watching it live. It was an abort engine start. Did they ever say why? It was for computer program.
I didn't go back and check. I don't know. At some point, I think it was the same attempt that they delayed a few minutes because there was a boat in the range, something like that.
It was that same launch. There was a boat.
So they delayed, and something else happened, of course, and then they, yeah. No, I didn't go back and check. I actually missed the 4th. I was going to look outside, but I missed it. So, and I don't know if you can really see from here. Okay. So, in a week we have homework 2. I'm going to tell you right away what it is, so you can start thinking about it, because you don't have the code to do it. You will have to do it. So last time we met, I talked about ground tracks, and I showed you that ISS ground track plot that I generated and how close it would get to Gainesville location on the map and at what time. So basically I'm going to ask you to do that in the homework too. So it's about ground track of the International Space Station with the state vector of February 20th and try to figure out in a 15-hour time window when you are the closest in terms of longitude and latitude to Gainesville. So it really shouldn't be that big of a deal. You have a lecture posted. When I do that, I don't know how much of the MATLAB code you can see, but it's really computing 2 angles at each time step of your simulation and correcting the longitude with the rotation of the planet. That's all you really need to do. And plotting things, of course, and finding, the minimum of difference between longitude of Gainesville and where you are and latitude. So it shouldn't be a huge deal. I'm telling you ahead of time, so you can go and watch the lecture. You can start doing it yourself. Because everything that I have used in that example, well, I will give it to you again, of course, in the homework. I don't know if it's still available online, because they keep updating the ISS orbital elements. But you should be able to figure it out ahead of time. So this is a huge hint. It's pretty much homework, too. So that's what we'll do. I have posted the seminar I gave at Daytona State College, in case you're interested. And I think that's all. Do you guys have any questions? Are you all up to date with uncollected homeworks and videos? I hope. Okay. So it's time to start talking about the fun part, which is maneuvering. Orbital maneuvers. Okay. So classifications, there's many. The drastic maneuvers are those where you're changing an orbit substantially. You are in low Earth orbit and you have to go to Mars. So at some point you fire an engine that puts you on a hyperbolic path that intersects with the trajectory of Mars, which we'll talk about. That's a big, drastic maneuver. Requires a lot of fuel, a lot of your mass on board, and it's a lot of accelerations. And then there are defined maneuvers, smaller ones. For example, what the International Space Station, well, the shuttle would do in the International Space Station during the last phases of rendezvous and docking. Those are very small jets that fire to adjust your trajectory to dock with the station. Those are not drastic maneuvers, right? You don't even feel them. You feel them a little bit maybe on board, but that's the first classification. What we're going to do to begin with, because we can do it kind of manually without necessarily using MATLAB too much, it's talking about impulsive maneuvers, which means that there is basically a burst changing your velocity without changing your position. It's of course an approximation. Your position is going to change. But we imagine, well, basically we're looking at drastic maneuvers here. We imagine that we have an engine that it's ejecting gases, and this is not a propulsion class, so all that part of modeling an engine is not for this class. But we know that we have something powerful enough to activate for a very short amount of time, have an effect, a big effect on the velocity, and the change in position is negligible. That's what we assume. Why do we do this? Because we can maneuver from an orbit to another if we assume that r is not changing. We don't need to integrate the equations of motion. If I give you a position at a given time and a velocity at a given time as vectors in Cartesian coordinates, at this point, you know you have everything you need, at least for an ideal Keplerian orbit, where the acceleration due to the planet is the following. If we stop at this model, we know that given these two, you have everything. You can compute orbital parameters. You can tell me the shape and orientation of that orbit in space and where the satellite is at all times. So you don't need any more information. The moment I change, I'll get that question in a second. The moment I change the velocity only, I'm changing the type of orbit where I am. So I decide right now I'm going to do something that changes my velocity so that instead of being on a circular orbit, from now on I'm going to be on a elliptical orbit. Yes?
Okay, so the changing velocity without changing your position, is that like a rotational maneuver?
No. Well, second, let me finish this introduction maybe. Maybe it will clarify. So changing V is a vector. You can change a vector in many ways. You can change the magnitude only. So if my satellite is flying that direction, I'm not going to change the direction of the vector. I change its magnitude, and that's called, I think, a pumping maneuver. I don't really care about this classification. But that is one thing you could do. You don't rotate anything. You just push it and increase the velocity, or retrofire and reduce the velocity. And it's still pointing in the same direction. It's the length of the arrow that is changing. That's a possible maneuver. Another maneuver is think it's called cranking maneuver, where you don't change the magnitude of v. We're not going to do this for a few days. Say that this is your velocity right now, and you just change it in terms of where it's pointing. So this is v before the maneuver, and this is v after the maneuver. The norm is the same. I have just reoriented the angle. That is what we're going to do for changes of planes, inclination changes, for example, not only. But the idea is that this occurs so quickly that if you were to integrate the equations of motion around those few milliseconds, I don't know what it is, seconds, that the engine is on, your position in space is not going to change that much. So you can approximate that it basically stays there. Again, we're talking about orbits that at least have a radius of 7,000 or so kilometers, right? Below that, below 6,378, you are inside the planet. So these are big trajectories. If you're finding something powerful for 1 or 2 seconds, or less, actually, I should say much less, it's probably not going to make a huge difference in percentage in terms of the position. So this allows us, as we'll see in a second, to really not use MATLAB, at least for a few simple maneuvers. Any other concerns about this? Another expression that you should know from propulsion classes, I believe, is the following. Delta m over m is 1 minus e to the minus delta v ISP. Am I writing a little too small? Probably. ISP G0. See if I have it in that form. Yes. Where, let me see, I can erase a few things around here. So again, we're going to target these kind of orbits, the ones where E and H don't change, right? This will be the spacecraft mass before the maneuver. The delta m, let's see what I call it here, well, it's the variation of mass. It's what you lose, right? Variation of the spacecraft mass due to the maneuver. So that's how much you're using in a certain way. It gives you an idea. And what's in here? So this is the norm of your maneuvers. Say that you're doing more than one maneuver where you change the velocity. Well, then delta v, to be completely accurate, is, say that you have n maneuvers. You sum up all the delta v's of those maneuvers. Because a delta v, in principle, is a variation of a vector, so it is a vector. Yes?
In that equation, is it e to all of that stuff? E
Yeah. This is exponential of all these things. This is the ISP. ISP, also called specific. You guys have taken propulsion? Rockets? Nothing? Okay. Specific impulse. That's all we need to know really for now. It's defined the following way. It's the thrust, T, that your engine can give you over, I'm calling it m dot. This is the consumption rate, how much mass that engine is ejecting when it gives you that thrust. And it's measured, this quantity is measured in seconds, as you can figure out. And it's basically giving you the efficiency of your engine. At the end, I'll show you something from the book because there is a nice image. But as you open this chapter, there is also a table that classifies the different types of engines that you can find. You go from solid, yes? Well, I was going to, one at a time. You guys go too fast. G0 is gravity at sea level, nothing special. 9.8, yeah. Gravity at sea level. And that's it. This is important, though, because, as I was saying, it gives you an idea of how efficient your engine is. Imagine if you have a thrust of, I don't know, I'm just making up numbers, 1,000 newtons, and a very small mass consumption for that, your ISP is pretty high. It's having a car that can give you a lot of performances without sucking up too much gas. That's really what it is, yes?
So for m and delta m, is that spacecraft, like the structure itself and
Everything. Yeah, this is what you had before the maneuver, right? Maneuver. Yeah. And this is the change. So basically, what you have used for the maneuver. Yeah. Yeah. So this is going to be, of course, an a-dimensional number. And so look at that table. You know, engines that bring things into orbit have usually ISPs of the order of hundreds of seconds, and they're not that efficient. They give you a lot of thrust. But imagine what the shuttle would do. The most of it was tanks and fuel, and all that stuff was used to go up. So the efficiency was not that great, but unfortunately that's what you get. You want a lot of thrust, you don't get a lot of efficiency. You use a lot of m dot, a lot of fuel. Then there are very small electric thrusters that people are putting on satellites. Those give you tiny forces for small corrections, and they use very little fuel. They have ISPs of the orders of thousands of seconds. They are very efficient, but the amount of thrust they can give you is limited. It's, you know, compare a Ferrari with a usual normal car. If you want to drive a Ferrari, you need to put gas, a lot of gas. If you want to ride on a Prius, then m dot is small, but you can push the accelerator as much as you want. You're not going to win. So that's really that's really what it is. It's performance. Just remember, it's in seconds, and it gives you performances of your engine. Of course, the bigger it is, the less you subtract here to that. So in general, a delta V that is above 1 kilometer per second, it's a big deal. If you stick in a typical 300 seconds, 400 seconds ISP in here, and you say that you have a delta V, bless you, of about 1 kilometer per second, this ratio is, say, I'm just giving you ballpark numbers, is about 0.25. That means you're taking a fourth of your mass, and you eject it to get the force you want. And we're going to look at an example in a second and give you an idea. And there is no refueling stations in space, even though we're thinking about refueling satellites. But maneuvers have to be planned carefully, especially when they are big ones, because for just one burn, you may use a fourth of your mass, a fourth of your tank, or more. So that's just an introduction. Let's look at some simple maneuvers where we can use this fact that, let me start here, that we don't, is the audio moving okay? All right, cool. Let's start with the most basic one, that is an Hertzmann transfer. Now these gentlemen here lived not too long ago. So these things that we're studying today are not that old. Okay, so a Hertzmann transfer is a two-impulse most efficient, and then we'll generalize maneuver basically between two circular orbits. We start simple with that just to show what we do, and then we'll generalize for now to elliptical orbits, still closed orbits. So this is what I want to do. For example, I am on a circle, my initial orbit. This is the planet, of course, so just call it the focus, right? Will be the center for a circle, or the focus for an ellipse. And I decide that I don't like that altitude, I want to go higher. At some point, my ability to do circles will degrade, of course. Okay, and say that this is R1, radius 1, this is R2. Okay, well, an Hertzmann transfer is performed the following way. You use, this would be a good idea to use different color. Which one was the best contrast? Yellow? Was it yellow? Do you remember? No, red? No, I don't think it was red. I think it was yellow, yeah. So you basically want to transfer your motion from this initial circle to a bigger circle, and things can be reversed easily the other way. So you want to go from A, this point, to B through what is called an Hertzmann transfer trajectory. I'll call this H. So you want to go from trajectory number 1, the small circle, to trajectory number 2, the big circle, and you do it flying on a transfer orbit, which is half of an ellipse. And what I'm going to do is basically the following. I am moving on this circle forever and ever, and at some point, at A, I turn on an engine that changes my velocity there, without changing instantaneously my position. And now, my new orbit that belongs to that combination of RA and V in A is not a circle anymore. My new orbit is this ellipse. And that's your first burn, first impulse. Once I am here, I am at the apogee. Of course, these should be tangent to each other. When I am at the apogee of this Hertzmann transfer orbit, I do another correction for the velocity so that I go into a circular orbit. Does it make sense? Now, it's easier done than said, as we'll see in a minute. Because we have the energy, that nice formula that we basically have never used, finally become useful. So what do we know about closed orbits for sure? We know that the energy is in general minus mu over 2a, where a is 2a is the distance, is the addition of perigee and apogee in case you have an ellipse. Otherwise, it's the diameter of your circle, right? Yes?
If we're assuming that the first circle is Earth's and the surface of the Earth, like what happens to space?
No, it's not, well, when you talk about this kind of transfers, you are already in orbit. We're not talking about orbital injection. That's a different story. I will have to, when you launch from the planet, as I said, most of the orbits are going, you're launching in the direction of rotation of the planet because you use that additional velocity, so it's a completely different problem. Here I'm already in a circular orbit. Okay. Yeah. So that is what we know. We also know that this is defined as v squared over 2 minus mu over r, right? Okay, and so everything we do for these impulsive maneuvers is based on that. As simple as that. So what happens at point, I want to use the same notation here. Yeah. What happens at point A? So at point A, I have two situations here. As long as I am on the circle, I know that the velocity at A on the orbit 1, which is the small circle, is what? Memories. You cannot throw away everything we've done in the first month. Unfortunately, you need it. Circular velocity is square root of mu over RA. And you're fine about forgetting this, but you need to be able to go back to the right page and check it out, unfortunately, at least that. That is velocity on a circle, constant. That's what it is. What if instead of being on a circle, I am on that elliptical orbit? And again, I just draw half of it because I'm not going to run on the entire ellipse unless I want to waste time. So the velocity at the same point A on H, the Hertzmann transfer, well, how do we compute this? Let's just apply that without skipping steps. Well, on that trajectory, I know that minus mu R1 plus R2 is equal to R1 plus R2 is this distance, right? Do we agree? So it's the, twice the same major axis. It's equal to what I'm trying to find, VA in H squared over 2 minus mu R1. Sorry, I called it R1. I should use R1. Okay. Correct this. I called it RA, but it's really R1. Okay, so from this one I can solve for VA. VAH is going to be equal to, let's see, square root of 2 times the square root of R1 plus R2. Let me put the mu here as well, why not? And what do I have on numerator? What do you think? R2, right? I'm just taking these, goes on the right hand side, common denominator, R1 plus R2 minus R1, I get an R2 there. So that would be the velocity you would have on an ellipse that H ellipse that has perigee at A, apogee at B. And so what do I need to do? Change it. This is where I am. This is what I want to be. Fire an engine that brings you to this velocity. Now, which one is bigger? Why? So basically I'm saying that delta V at A, it's a pumping maneuver. I hope we agree that I don't need to change the direction of the velocity, because here I was on a circle, so I was definitely normal to the radius that goes from the planet to A, and since I decided to go on an ellipse that is tangent to the two circles, I'm basically operating in the same direction, so I'm not going to change the direction of V, only its magnitude. And you guys are telling me that this second one is bigger than that one. I mean, you can compare, figure it out, but the reality is that, look at this. Energy is minus mu over A. I'm going to rewrite it here. Minus mu over 2A. So what happens as you increase the denominator? The energy increases. You want to go to bigger orbits? There is a minus in front of that, right? So as you make this bigger, which I am doing because the 2A for R1 was 2R1, now the 2A for the Hertzmann transfer is R1 plus R2, which is bigger than 2R1. So I'm going definitely on a trajectory with a higher energy. Don't get confused by the fact that this number is going down, but there is a minus in front. So I'm going to a higher energy, and I'm going to rewrite here that this energy is given by velocity squared over 2 minus mu over r. Since I'm not changing this piece when I do an impulsive maneuver, at that point A, I'm not changing it. With the maneuver, the only thing that needs to increase is the velocity. So yes, I agree. The velocity on the Hertzmann transfer at point A is bigger than the velocity on the circle, on the small circle. So you need to push forward, increase the velocity, and it's basically VAH minus VA1. That's your first impulse. And likewise, let's see what happens at B now. Before I even rewrite pretty much the same things here, I am going from the ellipse to a circle. What do you expect that it needs to happen to that velocity? So when I get to the apogee of the Hertzmann transfer here, I have a certain velocity that belongs to that orbit. I don't like it. I want to go on the circle, so I fire another engine and fix that velocity so that I end up on a circle. Do I push with the velocity or against the velocity? Why do I increase? Same reason. You're going from a 2A, so basically on the Hertzmann transfer, your 2A is what? Is R1 plus R2. On orbit number 2, my 2A is 2R2, which is greater than R1 plus R2. So I need to do another correction that increases the velocity. And if you want, we can just for completeness here, redo the calculations. So at point B, let me do the circle first. Velocity of B in 2 is, square root mu over R2. Okay? And you know what? I'm going to reuse that expression. Velocity B on the Hertzmann orbit is going to be equal square root of 2 mu. And here I should have probably something like this. You can do it yourself. Basically, in doubt, don't skip steps, redo this, restart from the energy. For all impulsive maneuvers, all you need to remember is that this is your start point. If you are in doubt, just go back to that. That will give you everything. Do an extra step. And so my second delta V in B, it's a positive one. It's, in this case, VB2 minus VBH. Now be careful with this. If I come up with another case where I need to retrofire, so I need to fire to reduce the velocity, when it comes down to computing the consumption, this one, remember what this is. That's the addition of all the norms. You don't subtract the delta V's. What if I have an impulse, the first one at 2 kilometers per second forward, and the second one at minus 2 kilometers per second, and you tell me that the delta V is 0, and basically you're doing those maneuvers for free? That's impossible, right? So remember that you have to add magnitudes. It doesn't matter if the first one accelerates and the second one reduces the velocity. You have to do magnitudes, okay? Yes?
So we're going from B to A, the opposite, would you just reverse?
Right. From B to A, what I would say that that's exactly what has happened, that I'm actually starting here. You just go on this other one. And everything is perfectly invertible. The maneuvers are going to have the same delta V's. The difference is that if I start from B, what do I need to do? Slow down. I want to go on the ellipse. When I get here, what do? Slow down again. So it's the same delta V's with the minus if you want. In terms of consumption, they give you the same amount of fuel that you have to use. In the first case, you're going bigger. The second case, you're going smaller. Nothing is free, though. I have an example here, because I want to generalize. These Hertzmann transfers are nice, but go circle to circle. We can really generalize and make everything that is involved here elliptical. The first one can be an ellipse, and the second one can be an ellipse, and in between, of course, you connect them with an ellipse. That would be the most general case that I may be able to attack today, or we'll do it next time, because I want to just look at some numbers for an example. Any other questions? So that's circle to circle. I'm actually going to do an example where I think my starting trajectory is an ellipse, and it's really not a big deal. You just do the same thing. It's just that instead of right away saying that that's the circular velocity, I will have to compute it with the energy, but it doesn't change the idea. Let's see what I have. This is from your book. I have a spacecraft that weighs initially 2 tons, 2,000 kilograms. This is a K. Okay? We'll figure out the consumption. Say that the ISP, it's 300 seconds. Okay. I start from, let's see what I have. Again, this is on your book, so you can look at all those problems. I am already on an elliptical orbit, and so the initial orbit, the way it's given to you, it's 480 times 800 kilometers. Now, what is that? You need to pay attention to the numbers that you create with calculations or that you are given. We're engineers. They need to make sense. If something doesn't look right, then you're not thinking through enough. Can this be radius? So the book tells you that this is perigee and apogee, right? So that's dimensions. 480, 800. That's the height, right? I mean, the book tells you that's the height, but you shouldn't have any doubts because both numbers are smaller than the radius of the Earth, right? So just to make sure, so this means that this perigee of my initial orbit is what? It's actually RE, radius of the Earth, plus 480, and that's one. And this other one is, let's see, RE plus 800. And again, these are kilometers, okay? And they want to go, well, there's two questions here. The first one is increase the apogee to 16,000 kilometers and then circularize. It's pretty much what we've done with the Hertzmann transfer, except I'm not starting from a circle. So this is what needs to happen, that I go, it's a 2-impulse maneuver that I'm trying to solve for. Nothing is to scale in this drawing, of course. Okay? I go on a Hertzmann transfer here, and my goal is eventually circularize at the apogee here, where this distance is now 16,000, well, RE plus 16,000, right? Okay. Well, what do you want to do? You need to find the delta V at, what do they call, A. This is A, and this is B. The first firing leads you to this. Let's call this orbit 1. Let's call this orbit 2. No, let's call it 3, just for fun. And this is 2. The Hertzmann transfer is 2. Yes?
How do you know that it started at perigee like that, or did you just assume?
No, you know that you're flying on a certain type of orbit, right? Maneuvers have to be timed. You need to plan to fire at that location.
Okay, so
Yeah, you decide when to fire. Yeah. One thing that we'll do, hopefully this week, is phasing maneuvers where, for example, we'll try to solve this problem. And then their timing will become very important. Say that, I don't know if this looks like a circle. It should be. Say that you are the shuttle here, right? And the ISS is on the same exact orbit, circular, and you want to reach it. So one of the maneuvers that you can do is go on an inner ellipse that being smaller is actually faster, and wait here. You can do it multiple times until the ISS is in the right location, and then go back to the circle. So timing is a major issue with these maneuvers. You need to know when to do them, basically in which location of the orbit. Yes?
that's 16,000 number. Was that just 1 by 2, or was it given, or?
I grabbed this from the book. It's on, it was in the book. Yeah, it's a problem in the book. Yeah. So basically, the goal of this maneuver, I'm starting from that ellipse, and I want to end up on a circle that has a radius of the planet plus 16,000. Okay, what do we do at A? Compute the two velocities that are involved here. What is the velocity of A on the original orbit? Do I have to do it with energy from scratch? Let's do it. Minus mu over, what is 2A for the initial orbit? It's 2RE plus 480 plus 800. That is my energy. And this is equal to velocity A1 squared over 2 minus mu. Radius at A, it's RE plus 480. Right? In that equation, you know everything. I'm going to give you the final number because you have calculators and you can do it. Mu is a given constant. Radius of the planet, again, is 6,378 kilometers and change. VA1 ends up being, if you saw from here, 7.7104 kilometers per second. Okay, so this is what I have, but I don't like it. I want to go on 2. I do the same thing. So this was what happened on trajectory 1, and I'm looking at the same point. On trajectory 2, I have a different semi-major axis, right? So now I'm looking at this yellow trajectory here that goes from A to B. The 2A is this distance A to B, and that is twice RE plus 16,000 plus 480. Agree? And this gives me VA on trajectory 2 squared over 2 minus mu. This is the same, because again, it's an impulsive maneuver. I'm not going to change the location when I apply these corrections. And I'm going to put it here. The velocity at 2 ends up being more or less. Do you think I am going to push or I'm going to slow down? Push, right? Again, you're going to a bigger orbit, higher energy. You need to accelerate. So it's 9 point. Is there any questions? Everything clear? Isn't this fun? This is fun. We're moving stuff around. You just give it a kick here and there, and it goes to a different orbit. It's great. That's what they do. Okay. So the delta V for A is, well, the difference between the two, this minus this, is 1.7226 kilometers per second. So this is a big maneuver. With that ISP, that takes a lot of fuel already. I will give you the number for the final consumption here, and it's going to be impressive. Most of this goes away. Half of your spacecraft almost is fuel to do this. So you can do this once probably, and then you're done. If you don't reach the right orbit, goodbye. And that's what happens. That's what happens all the time. If you miss and you don't have any more fuel, there's a lot of examples out there. You miss and you don't have any more fuel unless Superman comes and grab you. You're done. The DARPA had a project. It was a demonstration flight where they would rendezvous and dock two spacecraft. And one of the algorithms on board, I think, was incorrect and ended up using more fuel than needed. The two, they hit each other because one of the two didn't have any fuel left. So you need to be careful with maneuvers. Well, I'll move to the other board. For B, we do the same. Now, is B going to be slow down or accelerate again? You think? Well, let's just look at this. For the trajectory 2, the Hertzmann transfer, 2A is, what did we say? It's 2RE plus 16,000 plus 40, is it 480? Yeah. And then for trajectory 3, 2A is, what is it? It's RE plus 16,000 twice, no? So it's bigger. In terms of energy, it's higher energy, right? Yep, it's accelerating again. So B. Well, what happens at B if I am on the, I hope I can just move on now at this point. I'll just give you the values. Velocity B on trajectory 2, so the apogee of the transfer orbit, it's 2.8908 kilometers per second. Velocity B on trajectory 3, which is a circle, so this is now mu over this, right? Divided by 2. So it's actually without the 2, right? It's the radius, not the diameter, okay? So this will go here. It's giving me 4.22044 whatever kilometers per second. And so the second delta V, so this was my first one. The second one is 1.3297 kilometers per second, and it's increasing velocity, okay? So if I go back to my consumption expression, and I assume again that ISP is this value, which is a reasonable one. If you do the math of this, 1 minus exponential of minus delta V, so this is the ISP and this is G0, and now this delta V is the addition of this number and this number. Again, if this was a retrofire, it would not matter. You have to add magnitudes, remove the signs, because everything you do consumes fuel. Okay? Yes?
I have a question on notation. So VA1 and VA2, so like, is that like spatial awareness? Like, obviously you're starting at A and you're along path 1 and you're going to path 2. Is that what, I'm just trying to find the distinction.
Yeah. So V, it's velocity at point A. In the first case, I imagine that I am on trajectory 1. And then if I say velocity at point A 2, it's I am going to move on trajectory 2 from that point on.
Okay, so for V2, does that mean saying you're heading towards B?
Right, yeah. Okay. Velocity B2 is the velocity that you would have here if you remain on the yellow path, the transfer. So because if you don't do anything, this thing continues, right? And you end up here again, and you keep going in the ideal Keplerian world that, yeah. So, but I don't want to do that. I mean, you can if for some reason, say that, again, the intercept problem. Say that on this circle here, there is another spacecraft that is coming. And you want to intersect that spacecraft here, and say that you come here, we'll do this. You come here too early, and you need to wait another orbit. You can do that. So that's, yeah. But then at some point, if you have to end up on that circle, nothing will save you from that second maneuver. So yeah, velocity in B if you stay on path 2, and then velocity in B if you stay on path 3. Again, velocity and position, as far as we are concerned, they give us at every single time everything we need to know about an orbit. So if I give you position and velocity in A, I am basically deciding what kind of orbit I'm on. Yes?
So on the previous question where it was going from a circle to an ellipse to a circle, we decelerated for that delta VB, and in this case we...
No.
I mean, the change in V was negative? And then
No, they were both positive.
Oh, they're both positive.
Yeah. They were both positive. If we said, if you want to invert, say that for some reason you are going from bigger circle to smaller circle. And so now you're starting here and going down here. So this is what you're going to do this way. Then here you decelerate and then decelerate again. I think that's what we said, right? Any other questions? Okay, so what do you think this is going to be? I have a 0.64563, which means your delta M is, I don't know if I can fit it in here, is 1,291 something kilograms. Yeah. That's why the rockets are huge, to put into orbit small things, because the most of it is used with fuel. And the same with maneuvers that go from an orbit. If you go from LEO, low Earth orbit, to the geostationary one, it's a big maneuver. The most of your mass is going to be just fuel. Any questions on this? I'll start something that I will finish next time. So generalizing this means the following. What if everything that is involved now is elliptical? The start, the end. And when I say start and end, so far I've started from the small one and went to the big one. But again, everything is reversible. Just change the signs to your delta V's. Their magnitudes are the same. Okay? So say that I start from, in this case, trajectory 1, and this is called trajectory 2. I'm just trying to be consistent with the book, and the book changes the way they call trajectories. Yes?
When the shuttle undocked from the ISS and came back to Earth, did it use a Hertzmann transfer? Do you remember?
Well, that's re-entry. I don't believe you really are targeting another orbit. You're just going down with drag. So we haven't done drag yet. I actually have a question for you that you should think about. I'm giving you too much information, but when I did the ground track, for example, and I was talking about ISS, I did not mention any drag, right? Okay. So yeah, in that case, it's really not an Hertzmann transfer. Again, you don't do an Hertzmann transfer with the planet, because if you do the numbers, it basically means they're going to crash with the planet. So basically what you do there, we'll get there. We'll start doing, at some point, continuous thrusting. So what if now I cannot do impulsive maneuvers, but I actually have an engine that I turn on and it stays on for a long time? Well, the drag force is something similar. It's a force that it's always there. Once you start decaying and going to the atmosphere, there's no way you can get rid of the drag force. So it's a completely different type of problem where you have to integrate the equations of motion numerically, and it's like having an engine against you all the time. So definitely not an Hertzmann transfer. And again, even if you try to say, okay, I'm starting from 400 kilometers height, and I want to go to a circular orbit of radius 0, I think the numbers you will find will tell you that you're going to crash at a few kilometers per second with the runway, so you don't want to do that. Yeah. These are only things, problems where you are already flying at pretty high speeds. At least you are in LEO. Okay, so say that, let me give some, we're actually done here. So think about this. Start looking at this in the book. But if I go from this most ellipse to the big one, I can do it in two different ways, right? With a two-impulse maneuver. I can start at perigee and go here. I can start here and go here. So we'll see when it's more convenient to go on this one or on this one next time.